Hi, my name is Ariana, and this is my video lab report for Physics 2211 with Dr. Paducah, Lab 3, Black Hole. The purpose of this lab was to estimate the mass of a black hole by analyzing a star's orbit and then using the mass to predict the initial velocity a ship must have when it leaves the surface of a planet to fly around the black hole without crashing into it or the planet. The results for the mass of the black hole was 1.54 e34 kilograms. Using that mass, the initial velocity of this spaceship would need to be -8 e6 meters per second in the x direction and 1.1 e7 meters per second in the y directions. Here are some background concepts before we get into the lab. The first important concept is Newton's second law in the form of the momentum principle, which is used to derive the velocity update formula that is used in the computer model and seen below. It relates the net interaction between the system and the surroundings to the observed motion of the system. The formulas below were used in the computer models that predicted the motion of the object over time. The main force involved in this experiment is the gravitational force. The formula for gravitational force is shown above and also used in the computational model. The net force is the summation of the gravitational forces on the system, and using this idea, we're able to create an equation that will solve for the mass of the black hole. In part 1 of the experiment, the system was the black hole and the surroundings was a star. In part 2 of the experiment, the system was a spaceship and the surroundings were the planet and black hole. I assume since this takes place in space, the only forces acting on the black hole is the gravity from the star. The only forces acting on the spaceship are gravity from the black hole and planet, allowing us to set Fnet equal to Fg. Also in the code, we used final velocity as average velocity in the position update formula because universal gravitation is a non-constant force. We wanted to find the mass of the black hole based on a randomly generated star orbit and the mass of the star. I linked the rest of the code on this slide if you want to look at it. These are the initial conditions. The gravitational constant is 6.7 e to the negative 11. The star mass is given in the lab instructions as 2 e 30 kilograms, and then below are the time intervals to allow for a full orbit starting with t equals 0 seconds. Walking through the calculations, the part boxed in blue calculates dp over dt, which is then set equal to Fnet. The formula we introduced in the background portion of this presentation is Newton's second law, or the momentum principle. Next, we calculate the parallel and perpendicular components of Fnet to draw the length of the parallel and perpendicular components of the Fnet's arrows. Finally, we calculate the mass of the black hole using the formula we derived in the background portion of this presentation. Here are the final results. We averaged the different masses given over time to find that the mass of the black hole was 1.54 e to the 34 kilograms. We also gained information on the magnitude of Fnet and its components at the time the program ended. For part 2 of the lab, we used the mass of the black hole found in part 1 to predict the initial velocity a ship must have when it leaves the surface of a planet to fly around the black hole without crashing into the black hole or the planet. I linked the rest of the code in the slide if you want to take a look at it. Here are the initial conditions. The mass of the black hole is 1.54 e to the 34 kilograms, which we found in part 1, and the constant g stays the same. The mass of the planet is 9 e to the 28 kilograms, and the mass of the ship is 7 e 10 kilograms, which is given in the directions. The initial time and time step below and then to the right is the calculation for the planet's velocity. To begin the calculations, we calculate the force of gravity from the black hole and then from the ship to find Fnet on the planet. We then find the force of gravity from the black hole and then from the planet to find Fnet on the ship. These are the net forces we found previously to update the velocity and position of the planet and the ship, making them move. These calculations allow for the program to predict the motion of the planet and spaceship, so we can use guess and check to find a suitable initial velocity a ship must have when it leaves the surface of a planet to fly around the black hole without crashing into the black hole or the planet. After using guess and check, we found the spaceship should have an initial velocity of -8 e to the 6 meters per second in the x direction and 1.1 e to the 7 meters per second in the y direction to avoid both the black hole and the planet. The distance between the spaceship and the black hole, as well as the planet's orbital speed and period, were also calculated in the program. Possible source of error for this experiment is the limitation of a purely computational model. Also for part 1, the mass of the black hole is likely incorrect as it was the average of many different masses given over time. To gain a more accurate black hole mass, we could let the program run for a longer period of time. For part 2, the initial velocity obtained is likely incorrect or suboptimal as it was obtained through guess and check. So what does it mean? What are the differences between net force and its components and the rate of change of momentum in its components? The parallel component is the direction of an object's motion and controls the change in speed, while the perpendicular component is perpendicular to an object's motion and controls the change in direction. Fnet is equal to rate of change in momentum, and they are mathematically the same, but it is experimentally easier to observe and measure net force than rate of change in momentum. So what if? What initial velocity would the spaceship need to have to enter an orbit around the black hole without crashing into the black hole or planet? Through trial and error, I found that if the spaceship has an initial velocity of -1 e6 meters per second in the x direction and 1.1 e7 meters per second in the y direction, then the spaceship enters orbit around the black hole without crashing into the black hole or the planet. To orbit the black hole, the ship should have a similar velocity to the planet, but slightly different to avoid collision with the planet. Thank you.